What are the chances of catching a fish or catching some rays or catching a ball?
In your case, not very high. In maths, we call the chance of something happening probability, and it's expressed on a scale of 0 to 1. 0 means it will never happen. And 1 means it definitely will. So, for example, the probability of the sun rising in the morning is 1 because it will definitely happen. Whether you see it or not is another matter.
It's quite nice now, though. If I toss this coin, the probability of me getting ahead is 0.5, or half. Half the time we expect it to land as heads, and half the time we expect it to land as tails. Now, if I roll this die, what's the probability of me getting a 3? Now, obviously, there's 6 different outcomes, 1, 2, 3, 4, 5, and you guessed it, 6, and they're all as likely to turn out as each other. So the probability of me actually getting that 3 is 1/6.
Lynn Suzanne knows all about probability. She enters competitions professionally. Over the past 5 years, Lynn's won over £100,000 in prizes.
I've won 2 cars and I've won some super holidays. We've been to Amsterdam, Monte Carlo, South Africa, Cyprus, and a wealth of other prizes.
OK, so last year, how many competitions did you enter?
I must confess it was 500.
500? My goodness, that's more than one a day. And how many did you win?
I won about 10 major prizes last year.
We can work out the probability of Lynn winning a competition last year using this formula. Probability equals the number of successful outcomes divided by the total number of possible outcomes. Lynn won 10 competitions, so the number of successful outcomes is 10. The total number of possible outcomes is 500. That's the number of competitions she entered, which is the same as 1 over 50. So the probability that Lynn won a competition last year is 1/50th.
Lynn's favourite type of competition features tiebreaker slogans. Lynn knows fewer people will enter, so the total number of possible outcomes is lower, like on this packet of seeds.
Because you've got 3 questions to answer, but this is one where your skill comes in, which gives you a probability of success, and that's to write a tiebreaker slogan to say why you actually buy the seeds. Well, the secret to success is wordplay. So you notice it's to win a car, so you could have words like bumper, distributor, and super seeds. So you can have a slogan like, I grow these seeds because bumper flower show from a leading distributor supersedes all others.
I reckon it's yours. But this one looks quite exciting, Lynn. Tell us about this.
Yeah, it looks brilliant, doesn't it? Grab a grand. Wow. Is there £1,000 inside? Should we open it and have a look?
Yeah, go on.
If you open it and there's a little slip in there saying you're a winner, well, this is fantastic to win. But hang on a minute, there's probably millions of these sold up and down the country, so that the probability of actually winning it will be quite low.
One thing that it's important to realise with probability is that sometimes one outcome will stop another outcome from happening. Let me show you what I mean. If I roll this die and I get a 5, it means that I can't also get a 6 on that same throw. In this cupboard, I've got some tins of fruit. I've got some tins of peaches and some tins of prunes. Now, if I pick one of those tins, I'm either going to pick a tin of peaches or a tin of prunes. If I pick a tin of prunes, it means I can't pick a tin of peaches as well.
In this other cupboard, we've got 7 tins of food, and unfortunately someone's had the labels away, which is a bit annoying because we don't know what's what. What we do know is that some are in there. There are 4 cans of baked beans, there's 2 cans of semolina, and there's 1 can of dog food. Now, what I want to know is what's the probability of picking a can that won't go well on toast. Now, to look at these outcomes, we're going to use this tree diagram here. Now, we know that there's 4 cans of baked beans, we know that there's 2 cans of semolina, and we know that there's 1 can of dog food. 4 plus 2 plus 1 equals 7 cans altogether. Now, if there's 4 cans of baked beans and there's 7 cans altogether, that means the probability of picking baked beans is 4 over 7, or 4/7. If there's 2 cans of semolina, the probability of picking semolina is 2 over 7, or 2/7. The probability of picking dog food is 1 over 7, or 1/7. Now, you can always check your probabilities are correct, because when you add up the branches of your tree diagram, it should come to 1. 4/7 plus 2/7 plus 1/7 equals 7/7, or in fact 1.
Now, a tree diagram helps you to clearly see all the possible outcomes and the probability of each outcome. Now, I'm going to pick a tin of food randomly from this cupboard, and it's going to be random because I don't know what's in what tin. And then we're going to ask that question, which is, what's the probability of me picking something that doesn't go well with toast?
That's either the semolina or the dog food.
Now, the key to answering this is in the question. The words either and or are both in the question. And when that happens, you know you've got to use the or rule, which means you've got to add the probabilities.
So that means the semolina, which is 2/7, plus the dog food, which is 1/7. So that means the probability of picking either the semolina or the dog food is 3/7.
What do you think it is? Oh, yuck. Do you want to have that on toast?
Dog food.
OK, this is the bit where Ben and I both tackle a typical maths question, but only one of us does it correctly. The other makes a deliberate mistake, which you have to spot. You decide, do you tick it or do you trash it?
This week's problem is about picking out coloured balls from a bag. In this bag, we're going to put 2 blue balls, 3 green balls, 1 yellow ball, and 4 pink balls. What's the probability of randomly picking out either a pink ball or a blue ball?
Pens at the ready, go! In the bag, there are 2 blue balls, 1 yellow ball, 4 pink balls, and 3 green balls. What's the probability of randomly picking either a pink ball or a blue ball? Well, to help me work it out, I drew a tree diagram like this. Each branch represents the probability of picking out a colour. So I need 4 branches, 1 for blue, 1 for yellow, 1 for pink, and 1 for green. On each branch, I wrote down the probability of picking that particular colour. I've got 4 choices, so if there are 2 blue balls in the bag, the probability of picking a blue is 2/4. Yellow is 1/4, pink is 4/4, and green is 3/4. To find the probability of getting either a blue or a pink, I need to add the probabilities of these colours, which is 4/4 plus 2/4, which equals 6/4. And that's the same as 3/2.
Well, I've also drawn a tree diagram with a branch for each of the 4 colours, but I've worked out my probabilities differently. There's a total of 10 balls in the bag, so the probability of picking out a blue is 2/10. For a yellow, it's 1/10. For pink, 4/10, and for green, 3/10. To find the probability of getting either a blue or a pink, I need to add these 2 probabilities together. That's 4/10 plus 2/10, which equals 6/10, and that is the same as 3/5.
So, who is right and who is wrong?
Is Katie right to work out the probabilities as quarters?
Or is Ben right to work out the probabilities as tenths? Well, in fact, I was wrong because I made the mistake of writing the probabilities as being over 4, because there are 4 branches on the tree. In fact, it should be over 10 because there are 10 balls that we can choose from. A good way to check you've got your numbers right is to make sure that all the probabilities on the branches add up to 1. On my diagram, if I just go through that, I've got 2 plus 1 plus 4 plus 3, which is 10/4, and that is the same as 2.5.
We've probably all given in to the temptation of a prize-winning competition at some point or another. But did you know there are people whose job it is to set those competitions? Well, I've come to the marketing store worldwide to find out just what's involved behind the scenes in setting a prize-winning competition. Andrew, how important is probability to your job?
Probability is extremely important when developing competitions for 2 key reasons. Firstly, it's to understand how appealing a competition will be to a consumer, and secondly, how much budget or money that competition will take to run.
OK, so imagine that I'm a big crisp manufacturer and I want to set up a competition where I put £10 into winning bags of crisps, what advice would you give me?
The key is to understand how many packs you have and how many prizes you have to give away.
Okay.
For example, if you have 1 million packs but only one £10 prize, your probability will be 1 in 1 million.
Okay.
It will only cost you £10, but the likelihood of success is fairly low.
Very low, yeah.
At the other end of the spectrum, you may have 1 million £10 prizes, which equates to a probability of 1 million over 1 million, or 1 in 1. Every bag's a winner, but it will cost you £10 million.
Great for the consumer, not so good for me.
Maybe not.
Yeah.
Alternatively, one would look to find a more realistic compromise, which may be 1,000 £10 notes. So your probability is 1,000 over 1 million, or 1 over 1,000, which would cost you £10,000, which is a far more realistic figure.
I've got my big bag of crisps here, and with this I can win £10, but I've also managed to find a chocolate bar which has a competition, and that's to win a mobile phone. I know that the probability of winning the mobile phone is 1 over 25,000, and the probability of winning £10 is 1 over 1,000. Now what I'm interested in, because I'm very greedy, is what's the probability of me winning £10 and a mobile phone? Now the key word here is and. That means we're going to have to multiply the probabilities together. The probability of me winning a tenner is 1 over 1,000, and the probability of me winning the mobile phone is 1 over 25,000. So we multiply those together. 1 over 1,000 multiplied by 1 over 25,000 means the probability of me winning a tenner and a mobile phone to tell my mates about it is 1 over 25 million, which is tiny. It's minuscule. Might as well start eating, really.
Now remember our problem with the unlabelled tins of food. This time I've got a new set of tins, but I've decided to combine two independent events. Not only am I going to choose a tin of food at random, I'm also going to choose a piece of bread from this bag. Now the thing is, 1/4 of the slices of bread in this bag are mouldy and the rest of them are fine to eat. What I want to know is what's the probability of choosing a tin of food with something in it that's good to eat on toast, and, that's the important word, a piece of bread that's nice and fresh. Coming on to our tree diagram, you can see that I've added the second event, and that's whether the bread is fit to eat or mouldy. The probability of choosing a mouldy piece of bread is 1/4, and that means the probability of choosing a piece that's nice and fresh and fit to eat is 3/4. So what's the probability of choosing a can of baked beans and a fresh piece of bread? To calculate the probability of both happening, I need to use the AND rule, and that means multiplying the probabilities. The probability of choosing a nice can of beans is 4/7, and the probability of choosing a piece of bread is 3/4. That's a fresh piece of bread. So, 4/7 multiplied by the bread, 3/4, equals 12 over 28, which is the same as 3/7. Now all I've got to do is choose the bread and open a can of food. Oh, it looks like something gross, like, ugh, semolina. Let's see what's in the bread. Mouldy bread and semolina, yuck. What's the probability of those two things happening?